Hello, everyone. So this is the second talk of session 3 of this conference. We have with us Dr. Sagar Kalane. He is currently a postdoctoral fellow at the Institute of Mathematical Sciences in Chennai, and he will be speaking about discrete subgroups generated by two parabolic maps in rank 1 isometric groups. Over to you, Sagar. You may
Yeah,
begin.
First of all, thanks to the organizers for giving me such a wonderful opportunity to speak here in this conference. And as mentioned, I will talk on discrete subgroups generated by two parabolic maps in rank 1 isometry groups. These are the recent work with Professor I.D. Plattis, and I will also mention some works which are joint work with Professor Parker and Devendra Tiwari. So I will start with motivation behind the problem. So let capital G be connected Lie group and capital H be subgroup of G. Now it is very natural question that when H is a discrete subgroup of G, that means under the subspace topology inherited from G, when H is a discrete set. And this problem has long history dating back to Schottky and Klein in the 19th century. If you want to see quick examples of a discrete subgroup, then take G as a set of all real numbers. It forms a group under addition. And if you take H as a set of all integers, then it is a discrete subgroup of R. Now, another example will be if you take G as SL2R, these are the 2 by 2 real matrices having determinant 1. It forms a group under multiplication. Now, if you take H as SL2Z, then SL2Z is a discrete subgroup of SL2R. If you want to see non-example of a discrete subgroup, then take set of all rational numbers, which forms a group under addition, and inside R, it is a non-discrete subgroup of R. Now, if you take G as PSL2R, then any discrete subgroup of PSL2R is said to be Fuchsian group, and it is widely studied in the literature. And if you take target group as PSL2C, then any discrete subgroup of PSL2C is said to be Kleinian group, and it is also well studied. If you want to seek example of this Fuchsian group, then take modular group, that is PSL2Z, and it is a discrete subgroup of PSL2R. Now, in this last example, as I am saying that this PSL2R and PSL2C, now these groups PSL2R acts isometrically on a upper half plane, and PSL2C acts isometrically on a three-dimensional real hyperbolic space. Now question is that if you take higher dimension isometry groups, what are the discrete subgroup inside that? So if you take rank 1 isometry groups of non-compact types, then what are the discrete subgroup in that? We are interested to study that thing here. And it is well known that the rank 1 symmetric spaces of non-compact types are real, complex, quaternionic hyperbolic space over and Cayley plane over octonions. And the respective isometry groups in first three types are SON1, which acts isometrically on real hyperbolic n space. SUN1 acts isometrically on complex hyperbolic n space, and SPN1 acts isometrically on quaternionic hyperbolic n space. Now there is a isometric group of Cayley plane over octonions is an exceptional group, which is a F4 minus 20. Now there is one more reason why people are interested to study these discrete subgroups, because there is a relation between arithmetic groups and lattices in asymmetric spaces. And what is lattices here? Lattices is the discrete subgroup of G, where if you take quotient space, it has finite volume. And this due to Borel and Harishchandra, it is well-known result that all arithmetic groups are lattices if you take all symmetric spaces of non-compact types. Now, converse of this statement is true or not? This is a question. So, if you take any lattice, is this arithmetic or not? And answer to this question is given by Mosto, he constructed example of a non-arithmetic lattice in complex hyperbolic 2 space. And I will mention that this complex hyperbolic space is the only rank 1 symmetric space of non-compact type where this relation between arithmetic groups and lattices is not completely settled. And examples of a non-arithmetic lattices are only known in low dimension. That means I'm saying that PU, if you take PU n 1 and if n is less than equal to 3, then only examples are known. But if n is bigger than 3, then people are interested to construct non-arithmetic lattices in that group. So, as I mentioned, that lattices are the examples of a discrete subgroups. So, it is very natural question that to study discrete subgroup inside rank 1 isometry groups. And in this talk, I will mention some results in SP21 and SU21 here. So now I will give some background. So this H denote the set of all quaternions. Now S21 be the three-dimensional right vector space or H equipped with Hermitian form of signature 2, 1. Here Hermitian form of Z, W is given by W star iota Z. Here bold letter Z and W are column vectors inside H3 and W star is conjugate transpose of W. Here I am using iota is a Hermitian matrix having anti-diagonal entries 1, 1, 1 and other entries are 0. Now, due to this Hermitian form, we can define different models of a quaternionic hyperbolic space, but I will stick on this Ziegel domain model. Now, quaternionic hyperbolic 2 space is defined by set of all Z1, Z2 belongs to S2 such that 2 times real part of Z1 plus modulus of Z2 square is strictly less than 0. And if you see finite boundary points of a quaternionic hyperbolic 2 space, then it has description that 2 times real part of Z1 plus modulus of Z2 square is equal to 0. So if you add infinity point means projectivization of 1, 0, 0 vector. So projectivization of 1, 0, 0 vector, that is infinity point, together with these finite boundary points is the full boundary of a quaternionic hyperbolic 2 space. Now, SP21 contains all 3 by 3 quaternionic matrices which preserves defined Hermitian form. And this SP21 acts isometrically on quaternionic hyperbolic 2 space. Now, the full isometry group of quaternionic hyperbolic 2 space is PSP21. That means SP21 quotient out by its center, and its center is precisely plus minus identity. Now, I will state what is the classification of isometries here, and isometry in PSP21 is said to be parabolic if it fixes exactly 1 point from the boundary. Now, it is said to be hyperbolic if it fixes exactly 2 points from the quaternionic boundary of a quaternionic hyperbolic 2 space. And it is said to be elliptic if it fixes a point inside quaternionic hyperbolic 2 space. Now, you can see that this is a description of a finite boundary points of a quaternionic hyperbolic 2 space, but we can identify these finite boundary points with H times imaginary part of H. And we can give group structure on this H times imaginary part of H by this way, that zeta 1 V1 and zeta 2 V2 are elements of H times imaginary part of H. We define star operation by this way, and due to the star operation, H times imaginary part of H becomes a group, and we will call that group as Heisenberg group. Now, each element of Heisenberg group, we will assign parabolic isometry in SP21 by this way. Take zeta comma V in S times imaginary part of H, and we will define T zeta V as upper triangular matrix having this diagonal entries 1, 1, 1 and other entries are like this. Now, this T zeta V is the unipotent parabolic element which fixes infinity, and we will call it as Heisenberg translation by zeta comma v. Now, if zeta is equal to 0, then we will call it as vertical Heisenberg translation. And if v is equal to 0, then we will call such a translation as horizontal Heisenberg translation. Now we can define metric structure on this Heisenberg group by this way. We define distance rho naught between 2 points of a Heisenberg group by this way. And we will call this metric as a eigenmetric. And to this eigenmetric, we can define eigensphere. So what is eigensphere here? If you take Z naught belong to boundary of a quaternionic hyperbolic 2 space, then we take all Z belong to boundary such that distance between Z and Z naught is equal to R. Then we will denote it as SR Z naught. And what is SR Z naught here? It is a eigensphere with center Z naught and radius R. Now, if you take element of PSP21 which do not fix infinity, then we define isometric spares corresponding to that element, and we will denote it by IP. This isometric sphere IP is the eigensphere with center P inverse infinity and radius square root of 1 upon square root of modulus of A31. That means 31 entry of that matrix. Why I am defining this isometric sphere here? Because in the complex and quaternionic hyperbolic spaces, there are no totally geodesic real hypersurfaces. So constructing fundamental domains is very much challenging in these spaces, and we use these isometric spheres, which are the boundary bisectors, for constructing fundamental domains. Now, recently, Zhang, they consider subgroup generated by two particular Heisenberg translation inside PU21, and they studied when it generated a free subgroup. But there was some error in the result. So together with joint work with Devendra Tiwari, we gave counterexample to their result and we improved their result by this way. So you can see that these A and B are elements of PU21, where A is a horizontal Heisenberg translation by 2 root 2 comma 0, and B is a horizontal Heisenberg translation by 2 root 2 mu comma 0, where A fixes infinity and B fixes 0. Now question is that when subgroup generated by them is discrete and free. And we proved that if modulus of mu square is equal to minus real part of mu, which is greater than equal to 3 upon 128, then this group is discrete and free. Now it is I will mention that for proving this result, we have used Goldman-Parker-Schwarz theorem, and this you can easily observe that these are very particular types of Heisenberg translation, because these are horizontal Heisenberg translation. So it is very natural question. If you take any general Heisenberg translation with distinct fixed point, when they will generate discrete and free subgroup. And joint work with Professor John Parker, we gave answer to this question. I will mention this result very soon. But before that, I will talk about recent work in quaternionic hyperbolic spaces. So let A be Heisenberg translation by zeta 2 comma v2 inside sp21. This A fixes infinity, and B is a Heisenberg translation by zeta 1 comma v1 inside sp21, which fixes 0. Now question is that subgroup generated by them when it is free and discrete. That means we want to give conditions on zeta j and vj that ensure subgroup is discrete and free. And for this, we have used Klein combination theorem. I will state that theorem here. Let A, B are element of PSP21, and suppose dA be the fundamental domain corresponding to action of subgroup generated by A on the boundary of a quaternionic hyperbolic 2 space. Also consider dB be the fundamental domain corresponding to action of subgroup generated by B on the boundary of a quaternionic hyperbolic 2 space. Now these two fundamental domains dA and dB if they satisfy following two conditions, that dA interior intersection dB interior is non-empty and dA closure union dB closure is full boundary, then subgroup generated by AB is discrete and isomorphic to subgroup generated by A, free product with subgroup generated by B. Now we use this theorem for proving our results, and our recently joined to work with Professor Plattis, we gave this result that if you take consider these two Heisenberg translation, one fixes infinity, another fixes zero, then subgroup generated by them is free and discrete if any one of the following three condition is satisfied. So our first condition is that k zeta 1 v1 times k zeta 2 v2 is greater than equal to square root of 2 times f zeta 1 v1 times f zeta 2 v2, where k zeta v is square root of modulus of this mod of zeta square plus v, and f zeta v has this description. Now our second condition is that modulus of zeta 2 times k zeta 1 v1 is greater than equal to this quantity, and our third condition is that modulus of zeta 1 times k zeta 2 v2 is greater than equal to this quantity. Now for proving this theorem, we have used Klein combination theorem, and we constructed different fundamental domains which will be applied to this Klein combination theorem. So I will mention that for constructing first result, we have used isometric spares, and I will prove this. I will give sketch of proof of that first result, how we are getting this first condition here. So as I mentioned, B is the isometry which fixes 0. So B inverse is, will also fix 0. Now we can define isometric pairs of B and B inverse, that IB and IB inverse respectively. Now you can observe that 0 is the common point in between them, because I draw this picture that red color circles are the isometric pairs of IB and IB inverse, and 0 is the common point between them. Now our claim is that to find big eigensphere which contains these both isometric pairs, and so we need to find this radius dB and center 0 such that these both eigenspheres, both isometric spheres contain inside that bigger one. And for that we proved that if you take dB as 2 raised to 1 by 4 upon k zeta 1 v1 times f zeta 1 v1, then center 0 and with respect to that radius, these isometric pairs of B and isometric pairs of B inverse are contained in that bigger ball. Now I will mention that what if you take subgroup generated by B on the its action on the boundary, then fundamental domain corresponding to that is the exterior of these two red circles. If you take exterior of these two red circles, then this is a fundamental domain corresponding to action of B. Now our claim is to that find fundamental domain description for A, but A has fixed point infinity, so we cannot apply directly that we cannot find out isometric pair directly. But if you conjugate A by iota, then iota A iota is matrix similar to B, and we can apply similar construction, and so by the similar argument, the isometric pairs of iota A iota and iota A inverse iota are contained in the bigger ball of radius dA and center 0. Now for getting our fundamental domain, we have to see the image under iota of these isometric pairs, and it is contained in the exterior of a eigensphere with center 0 and radius 1 by dA. It is due to, if you take iota action on the eigensphere with center 0 and radius r, it will map exterior of this eigensphere to interior of a eigensphere with center 0 and radius 1 upon r. And due to this fact, we have this thing. Now we have description of fundamental domains. So for applying Klein combination theorem, we must have this fundamental domain must satisfy these two conditions. And for satisfying these two condition, we must have condition that dB is less than equal to 1 upon dA. So if dB is less than equal to 1 upon dA, then you can apply Klein combination theorem, and due to this, we will get our first result, this one. Now, if you restrict these entries, these are the quaternionic matrices. If you restrict it on complex case, then we will get results which we already proved in the joint work with Professor Parker. So you can think these are the generalization of SU21 work. So I will mention some results of SU21 work here now. So let A be the Heisenberg translation by S1 e to the power I theta 1 comma T1. This A is a Heisenberg translation inside SU21, which fixes infinity. And B is a Heisenberg translation inside SU21, which fixes 0, which is a Heisenberg translation by S2 e to the power I theta 2 comma T2. Now question is that under which conditions on Sj, Tj, theta j, subgroup generated by AB is discrete and free? And answer to this question is given by the joint work with Professor Parker, that it is free and discrete if one of the following four condition is satisfied. Our first condition is that square root of modulus of S1 square plus IT1 times square root of modulus of S2 square plus IT2 is greater than equal to this quantity. Our second condition is that if S1 is not equal to 0, then S1 times square root of modulus of S2 square plus IT2 is greater than equal to 2 if S2 is 0. And if S2 is non-zero, then it is greater than equal to this quantity. Now, if S2 is not equal to 0, then square root of modulus of S1 square plus IT1 times S2 is greater than equal to 2 if S1 is 0. And if S1 is not equal to 0, then it is greater than equal to this quantity. Now, if both S1 and S2 are non-zero, then S1 times S2 is greater than equal to 4 cos cube theta 1 minus theta 2 by 3. And for proving this result, we have used again Klein combination theorem, and we have constructed boundary this fundamental domain by using boundary bisectors. One of the boundary bisectors I defined already. Now, this our first condition looks very big condition, but if you take S1 and S2 0, then it becomes, if you take S1 S2 0 here, then it becomes vertical Heisenberg translation. So we get this corollary that if you take two vertical Heisenberg translation, then subgroup generated by them is discrete and free if square root of modulus of T1 times square root of modulus T2 is greater than equal to 2. And it is proved by Professor Parker in this paper earlier. He proved result for P in 1, but he took vertical Heisenberg translation in that paper. Now, also I will mention that here, this right hand side of this equations, it involves Sj and Tj, but we can eliminate Sj, Tj, and we will get weaker version of our theorem. So subgroup generated by AB is discrete and free if one of these three conditions is satisfied. Our first condition is that square root of modulus of S1 square plus IT1 times square root of modulus of S2 square plus IT2 is greater than equal to 4. Our second condition is that S1 times square root of modulus of S2 square plus IT2 is greater than equal to 4 cos square theta 1 minus theta 2 by 2. And analogous to this, we have this third condition, S2 times square root of modulus of S1 square plus IT1 is greater than equal to 4 cos square theta 1 minus theta 2 by 2. And these are the references. This first, in the first paper, it is joint work with Professor Parker, where we solve result for SU21. And in the second paper, this is the joint work with Devendra Tiwari. We gave this result on horizontal Heisenberg translations here. And it is a this recent work with Professor Plattis on the SP21 case. Thank you.
Thank you, Sagar, for the nice talk. Any questions?
What happens if you have 3 generators?
Sorry, I didn't get
An
it.
A, B, and a C.
A, B, and C. Yeah.
So if you generate a
So,
subgroup by 3,
yeah, it is very interesting question actually. We recently think on that actually. So it will be somehow difficult question, but I will give I will tell you one thing that there is a paper by Richard Schwartz that he solved Goldman Parker conjecture there. So if you take 3 elements I1, I2, I3, these are the reflections around this complex geodesics. Then it forms a triangle group actually. So he gave result on this triangle group is discrete and free. That thing. If and only if there is a condition on angular invariant. So this result I know, but very other than that, for 3 generators, we are interested actually for looking that problem. Yeah, thank you.